out, so one of my students bought it for me. Okay, they're throwing it out. Okay,
Those
ready,
were also-
Brian? Okay.
Those are also the ships that they could build in like 3 days or something like that, wasn't it? Like they were
2 weeks. They were from laying of keel to, steaming out of the harbor. It was like 2 weeks. It was like 1 week from laying of keel to floating the ship, and another week to outfit it and everything, finish it out and outfit it. But it's 2 weeks. But they were fair-sized ships. I mean, they were like 15 or 20,000 tons, so it wasn't a small ship. But pretty amazing that you could go soup to nuts in 2 weeks. Anyway, we talked about flames, and the temperature of flames is determined by the enthalpy of the reaction, the oxygen-fuel ratio, and the presence of inerts, whether you got nitrogen or something there. And in fact, pure oxygen flames have about 10 times the heat intensity of the same fuel burning in air. So even if I have propane here, and this is a pre-mixed flame burning in air, that's not anywhere near as hot as if I was using pure oxygen. And I had an oxygen tank here, I could get a lot hotter, so far as that goes. That propane will not melt steel with an air flame. Actually, propane has a hard time melting steel. You probably could. You can certainly melt aluminum or copper with propane. But steel melting higher, you have a hard time with propane. But with MAC gas or acetylene, you can melt steel. The gas boundary layer greatly limits the temperature of this whole thing. And I actually found my old overhead of gas boundary layers. I drew you a gas boundary layer before, but here it is in PowerPoint glory or whatever. Anyway, you have the gas coming in, you have a solid surface, and as the gas goes across here, you have a relatively stagnant layer of gas, and it has to diffuse across here. And it turns out as the heat diffuses across here, you will lose 90 to 98% of your heat. It will just go up basically as hot gas, heating up the welder, the person doing the welding, as opposed to heating up the workpiece. Only 2 to 10% of the heat gets in here, which means the process is only 2% to 10% efficient. You're losing 90 to 90%, 98% of the heat just to the surroundings. So not a terribly efficient process in terms of getting heat into the workpiece, but nonetheless one that we use particularly for training, and also the equipment cost is low. We talked about that. I kind of showed you this overhead, which is the cost of welding and equipment cost dollars per pound versus productivity. Flames are way down here. You can get the equipment for less, $1,000 or less, whereas arc welding, it might cost you $5,000 or $10,000. Laser and electron beam, you're up around $1 million. The interesting thing is resistance welding, which is the way we put cars together, is relatively inexpensive compared to its productivity rate in terms of feet of weld per minute or whatever, or per second I have on here. And that's actually one of the reasons why they use resistance welding in automobiles. It's a very low capital cost type of process. So anyway, the gas boundary layer is important in limiting the heat transfer of these low heat intensity processes, and we're going to find that arcs actually get around part of that gas boundary layer problem. Acetylene produces 36% more useful heat for melting steel than C3H4, and I had there was a little calculation that I had done. Here it is. Here it is in its overhead glory. Acetylene melts at 3100 C. MAP gas C3H4 is 2870 C. If you take the square of that, remember the combustion intensity goes as a square, you get 36% greater, based on this T squared approximation, 36% more heat from acetylene into a steel surface. The steel surface, you remember, it's 3100 minus 1600 degrees centigrade for the melting temperature of steel. It's only the useful heat above the melting temperature of steel that's going to be useful in melting steel. Okay. So anyway, that's one way to look at it. One of the problems today is we no longer have, as of beginning of March of this year, the one company in Canada that was making MAP gas is out of business, and so now, if you go to the hardware store, unless you buy some old tanks, and don't go to the hardware store in Belmont, I bought out all 11 of their old tanks of MAP gas. These are the little ones. And I had Harold Larson go to Home Depot and buy out all of theirs. And so what you'll now see is something called MAP Pro. And MAP Pro stands for propylene. And it doesn't have a double P, actually it does, it has MAP and then propylene, so you think it has a double P, but it doesn't have a registered trademark next to it, because it's not propadiene, methylacetylene, these two. Here's acetylene, triple bonded carbon, and you complete the bonds with 2 hydrogens, C2H2, here's propadiene, 2 doubly bonded carbons, 3 carbons in chain, and then you complete with 4 hydrogens. Methylacetylene is basically the same thing, except instead of 3 carbons with double bonds in between, you have 3 carbons with a triple bond and a single bond. And this one is actually a methyl group, and this is acetylene. So this is one end of the, instead of having a hydrogen off this carbon, you have a methyl, so it's methylacetylene. It has the same formula, and in fact, the chemist might tell you that these things are sort of on a nanosecond time scale, might even transform one to the other between these. But basically, it has the same type of heating value because carbon has a higher heating value than hydrogen, and the more carbon you can get in there, the hotter it's going to be. Today, MAP Pro, if you go to the hardware store, is going to be propylene. Propylene is C3H6, so we've gone from a carbon-hydrogen ratio of 1 to 0.75 to 0.5, and propylene is 3 carbons with 1 double bond. Here's your, you can think of that as the methyl group, if you will. This hydrogen makes this carbon happy with 4 bonds, and this carbon over here has 2. Polypropylene basically it's something where you get rid of that double bond and you end up making an infinite chain with three carbon bonds. You essentially polymerize that double bond to a single bond, and you end up making something that has a formula the same as candle wax. Okay. But polypropylene, you're trying to get these double and triple bonds in there because they have more energy content for generating enthalpy of reaction. Yep.
For that one diagram talking about the boundary layer over the plate you're welding,
yep.
Was there ever anything done to try and disturb the boundary layer so you get like a more focused heat into the narrow area?
One of the things you can do is remember the combustion intensity was related to the square. One was the velocity and one was the enthalpy of the reaction. Well, the enthalpy of the reaction, I'm just trying to get more double and triple bonds in these hydrocarbons to get higher velocities to disturb the boundary layer or make a thinner boundary layer, if you will. I'm trying to get a higher velocity, which gives me a thinner boundary layer. And that's where I go from a diffuse flame to a premixed flame to a jet burner. Remember, the diffuse flame, basically the fuel and the oxygen come out, but they mix in the air, and it's sort of a wispy, like your fireplace. Or you just have fuel coming out and the oxygen comes in, and it's still sort of a wispy fire. Okay, you're just squirting fuel on something. A premixed flame, which is what these tanks of propane and MAP have down here, you mix the fuel in the air in a chamber, but you send the unignited mixture out here to burn at constant pressure in the atmosphere. That's about 1 to 10 times the velocity of a diffuse flame, and the boundary layer gets much thinner, and you'll get much greater heat intensity because of the high velocity. If you go to a jet burner, which we don't use in welding, well, actually we do. I'm going to talk later about plasma arc welding, and plasma arc welding is sort of a jet burner. But you mix and ignite the fuel in the air in a constant volume chamber, and it comes out at very high velocity. It's roaring out of here at like 180 decibels. You got to wear earplugs, or you're going to lose your hearing. Okay, coming out of here just like a jet engine. That's very high velocity. Another 5 to 10 times the velocity of a premixed flame. These gases are coming out near sonic velocity. Okay, that's the thinnest boundary layer you can get, unless you do one of the tricks that we're going to talk about There's two tricks to get even thinner boundary layers, and we actually use them, but that's the rest of the story that I'm going to get to in a little bit. Okay, but before I get to that, so if you hold off on that, other questions on this? I was going to tell you about these two compounds. Anybody know what this one is called? N2H4?
Laughing gas.
Pardon me? Laugh? No, it's not laughing gas. What someone else said? Pardon me? Hydrazine. So is that what you were about to say?
No.
Okay. Anybody know what hydrazine is for?
Yeah.
No nukes here? Yeah, okay. What's hydrazine used for in the Navy?
It uses a weak base.
A weak base? Well, okay, yeah, okay. You might think of it as that. When you boiler water scavenge oxygen from boiler water. One of the problems with nuclear reactors, actually with everything, is everything corrodes. If there's oxygen around, it will corrode. And fortunately, when the reactor is up and running, it's boiling water, it's hot water, and there's not a lot of oxygen dissolved, so corrosion doesn't really occur when the reactor's hot. It's when you start up. It's just like the wear on your car doesn't occur when it's running down the highway, heated up, you know, and going 60 miles an hour down the highway. It's when you start it up cold and the oil is not really bathing that whole engine. 98% of the wear occurs on startup of that car, okay? It's not while it's running. The oil does a good job while it's running. It's when it's getting started up. Same thing with corrosion on boilers and reactors. You had a question?
Do you know what the hydrazine was used for in that satellite that was shut down?
It was probably used as some sort of fuel, okay? But I'm not positive on that. In fact, actually, it might have been used as a gas generator up there. You know, when you have satellites, you want to position them a little fine-tuned positioning. And so the hydrazine might have been something that's unstable enough that it actually generates more gas. I'm not positive. I don't know, okay? But hydrazine is well, it's got hydrogen and nitrogen, both, and it wants to decompose. It's not the most stable thing in the world. And so it will react with oxygen that's present and take the oxygen out of the system. Now, in commercial nuclear reactors, we do things like we put the water through a steam generator to keep it hot and boil the water off so that the fish can't breathe. Okay, if the fish can't breathe, then there's no oxygen in the water. If there's no oxygen in the water, I guess the fish can't breathe is the proper way to state it. But in any case, hydrazine is very expensive. Only the Navy can afford to use it in reactors. But whenever you shut down the reactor, you basically fill the vapor space above the water when it cools down with hydrazine to keep corrosion from occurring, keep oxygen from dissolving in the water and getting in and corroding your reactor, because your reactor is going to corrode when you're in, when you're in shutdown mode. And so the Navy actually uses hydrazine, which is the best material, but it's also very expensive. Commercial people basically heat their water or use a vacuum to pull the oxygen off and things like that. But as I remember, the Navy's still using hydrazine in their reactors. Okay, so that's hydrazine, not useful for welding necessarily. This C2N2, which is sort of like acetylene. Remember, acetylene is triple bonded carbon with two hydrogens. This is a triple bonded carbon with two nitrogens. And the carbon-nitrogen bond has even a higher energy than the carbon-hydrogen bond. And so you can actually get higher temperatures by burning this gas. One of the names is oxyacetylene or something, but another name is cyanogen. CN is cyanide. And this is cyanogen, which means it's a gas of cyanide. And that's one of my students. I still have the sheet he gave me right here somewhere. From years ago, this guy was a nuclear reactor guy. He says he looked up the compounds in cyanogen, or oxalodinitrile. And the dictionary says it's cyanogen. It's used as a rocket propellant, a fumigant, a military poison gas, and a welding gas. Okay, so that's why we don't really use it too much as a welding gas. But in the old days, when people were trying to get the highest temperature gases, they would use things like Cyanide, but you had to have nowadays you have to have a health physicist standing over your shoulder. Now what do we do to get higher temperatures, greater expansion, greater velocities for rocket propellants or other things? If these are about the highest temperature gases we can burn. And you go to solids. And what do you do for solids? It's not rocket science. Actually, it is rocket science. But what do? Just like sparklers, you use metal powders, aluminum and magnesium. So if you take a sparkler, I'm not going to light it here. It's an uncontrolled. I mean, I don't mind my controlled flames, but I think that I don't want to be like the station nightclub and get in trouble. But in any case, you can actually see the shininess of this. It's got aluminum or magnesium powder. Now typically they use special powders, have lots of surface area, so you can ignite it. If you actually ignite a sparkler, you actually see when you're all done, first of all, it's got a steel wire core. And that wire core does not melt, even though the temperature of that reaction is 4,000 degrees centigrade. There's not enough mass in those little powders to melt that steel core. Plus, when you're all done, you'll find a lot of clay. Basically, that's got a lot of clay in it as a binder. They want to see little sparks come off, and those are the burning powders. But most of that is just clay. They made up a mixture of metal powders and clay, and you start it off, and it basically is sort of a thermite reaction. There might even be some iron powder in there to help get it going, or iron oxide in there to help oxidize the iron powder. But if you do the 4th of July fireworks display here, you know, in the Boston Pops, most of those fireworks are metal powders, aluminum and magnesium powders that are burning up there to magnesium oxide and aluminum oxide. Really high temperature flames, 4,000 degrees centigrade, whereas acetylene will only give you 3,100 degrees centigrade. So you can get higher temperatures in solid fuels by using metal powders. Okay? But the problem is, if you're not careful and they ignite on their own, you have a fire you can't put out. And actually, you brought me the book of naval disasters, but I've purchased a copy for $10, and it actually has pictures of the Belknap, okay, which was this destroyer that was in the Mediterranean. I've learned a lot of things more from that book about the Belknap. It was the Forrestal that ran into, and we'll look at those some other time, okay, when I get the book. You can still buy it. It's only $10. That's that stuff. So now let's talk about cutting, unless there's other questions about flames in general. And we generally don't use oxyacetylene flames unless you're maybe a plumber, because the productivity, you're talking to melt just the width of that weld pool, which might be a half a centimeter to a centimeter, might take you 5 or 10 seconds of holding the torch there. That's a very slow process. But it's a process we tend to train people on. I remember about 20 years ago, I walked into the lab and I had a couple of undergraduates and graduate students. They're all standing around one of the tables over there using the oxyacetylene torch. I said, what are you guys trying to do? Or what are you guys doing? And they said, oh, we're trying to oxyacetylene weld. And I looked at them, these were terrible looking welds that they had done. I said, well, let me show you how. And so I took the torch and I laid down this beautiful looking oxyacetylene weld bead and I said, that's how you do it. And I walked away. None of them knew that was the first time I had ever oxyacetylene welded. But I knew the thermal time constant, that you got to go slow. And they were trying to go too fast. And so they'd melt and then they'd try to move it and they'd lose their heat. You got to carry the heat along very, very slowly. You got to be patient. And I knew from the science that you had to go slow. So I was able, first time I ever oxyacetylene welded, to put down a beautiful looking weld bead. That's one of the reasons that people train people on oxyacetylene welding. If you can teach them to go slow, they can get their confidence up, and it's just like we talked about the video game and the $100 bill bar game of, you know, can you catch Ben Franklin's nose and stuff, right? It's a hand-eye coordination thing. With arc welding, a lot of places they'll start you out with arc welding, but it's like starting on the intermediate level of the video game. And you're going to make lousy looking welds until you get enough proficiency. And I don't weld arc weld enough, I still have to go out there and practice a little bit, because I don't do it every day. If I do it once a month, that's frequent for me. And I have to kind of go out there, and it takes me a couple of strikes of the arc before I start getting back to the hand-eye coordination.
When did you learn to weld? Did you do that after you got your degree here, or is that something you learned in high
Well,
school?
you wouldn't learn anything practical like welding here. Actually, I did my thesis in superconductivity here, which is an appropriate thing to do at MIT. And I actually took a course in welding, started to take the course in welding, but I decided the professor didn't know what he was talking about. And so when I went to work for Bethlehem Steel Corporation in the research laboratories, they put me in the welding group. So all of a sudden, I was a welding engineer. I knew nothing about welding. And I would go up, we had 4 engineers and 4 technicians, and I went to the technicians and said, teach me to weld. And so they gave me some electrodes and a piece of steel and a mask, and they said, this is how you start the arc, and they walked away. And so that's how I learned to weld. Okay? Now every now and then they come up and laugh at how I was doing. Okay? But that's how I learned to weld in my first job. And so ever since then I've been a welding engineer. Okay? Never had a course in welding, but I do teach courses in welding. But I'm not a certified welding engineer, but there's a reason. It's because I wrote some of the questions and I graded the exams for the certified welding engineer. So I don't think I should take the test. But anyway, but I've never. Okay, there's actually only one school in this country. You've already heard that. You should have heard that stuff and other things about it. There's actually 2 schools, Luxorno in Texas and Ohio State, that actually give degrees in welding engineering, 4-year degrees in welding engineering. There's a number of other schools that give associate degrees, like 2-year or 3-year degrees as a welding technologist. But in general, in this country, there's not a lot of welding engineers. I remember the chief welding engineer who's passed away now down an electric boat 25 years ago used to say that Ohio State graduates were neither fish nor fowl, meaning welding engineering graduates, because they weren't really mechanical engineers, they weren't metallurgists, they weren't civil engineers. They knew a lot about, they knew a little about a lot of things, but not much about anything. And so there's a debate about whether you should just be a mechanical engineer and be taught welding, or materials engineer and be taught welding, or whatnot. I don't know if it really matters, but you do have to study it, because the physics is a little different. And I always think it's interesting. Anytime some physicists, welding creates big problems. Take the Seawolf submarine, okay? All of a sudden they had the ship 18% built, and they found they had to start all over again and rip it apart. And it cost about $500 million. Well, that's not the first time someone's had a welding problem that costs a lot of money. It happens in industry as well as the Navy. And when that happens, management will take some physicists and say, you're now a welding engineer. Go out and study welding, and we're going to spend money so that we don't have these problems in the future. Well, one of the first things that a physicist does is he says, well, I can measure the temperature of the arc. And we're going to learn later, in the next couple of days, that the temperature of the arc is not a useful number. Okay, you can do it, you can measure it. And this research is redone about every 5 years by someone who doesn't bother to read the welding literature, okay, or take my course. Okay. Anyway, let's talk about cutting, unless there are other questions. Cutting. So it turns out you can use these high heat intensity processes to cut. And on here we have oxyacetylene cutting. Well, actually we have oxygen cutting over here. This is oxyacetylene welding. We have oxygen cutting over here. This is arc welding, and somewhere in here we actually have plasma cutting. Now, oxyacetylene cutting is actually an intriguing process. Okay, you take it's not really you don't really worry about whether it's oxygen or acetylene or propylene or MAP gas for your cutting. It's actually oxygen. And if you went to a steel mill today where they do continuous casting and they have these they pour the steel into the mold, and they have these bands of hot steel, glowing red hot or red yellow hot, coming out of the mold, and it's soft enough at that point they turn it into kind of a 90-degree bend over with about a 100-foot radius. And this thing might be 6 stories tall. In order to have a 100-foot radius, you cast it vertically, but then you have to take it out horizontally, so you bend it with these rollers. And it turns out you have to now cut it, because you're going to make a continuous band of steel. You're going to cast this continuous band, and you're going to cut it into what we call fillets or blooms, okay, which are just big plates of steel that you're going to later roll into sheet and plate and bar and whatnot. You have to cut it. Well, it turns out they don't use oxyfuel cutting, they just use an oxygen lance, because the steel is already hot. And all they have to do is go in there and blow a jet of high velocity oxygen on the surface, and they will burn right through the steel. And they often call oxyacetylene welding or cutting burning of steel, because you literally are burning the steel. You're going to burn right through it. Ordinarily, you have a problem of this gas boundary layer. So you have in this case, a jet of oxygen is going to be hitting the surface of the steel. And the surface of the steel has a surface coating, and it more likely than not will be Fe3O4. It could be FeO, it could be Fe2O3, but this is the steel. And if this is coming out of a continuous casting furnace, this could be 12 inches thick, okay, piece of steel. And this iron oxide on the surface might be a few thousandths of an inch thick. Probably no more than 10 thousandths of an inch thick, a few human hairs thick. But basically it oxidized in the air, and you can't cut through the iron oxide. However, pardon me?
Stuff rusts that fast?
It's not rusting. This is Fe3O4 is called mill scale. It will oxidize that fast. Now you haven't had enough of the first part of the course where we actually talk about how long it takes for oxygen to hit the surface of fresh metal. 10 to the minus 8 seconds. Okay, did you get to that yet? Okay. So it doesn't take long for oxygen to hit the surface. And when it's this hot, you will grow a mill scale on there a few thousandths of an inch thick within seconds. Now, it doesn't keep on oxidizing because the oxide layer becomes a protective layer that protects the rest of this from oxidizing. But if you hit it with the jet of oxygen, this is so hot, and the melting point of this is a little bit below this. Actually, I have the data here. Just happen to have flame cutting. For iron oxide, the melting point of the oxide is 1380 C, the melting point of the metal is 1536. So iron oxide actually melts below the temperature of the melting point of iron. And so I actually can melt the surface of this. If I hit it with a pure oxygen jet, I can melt the surface, blow away the liquid iron oxide, and expose steel, unoxidized steel, to pure oxygen at 1500 degrees centigrade. Well, what's it going to do? It's going to oxidize. When it oxidizes, it gives off heat, and it will be molten iron oxide. So I blow away that iron oxide, and I just drill a hole through here in about 10 milliseconds. Okay? What happens when I'm oxyacetylene cutting, if I brought in a torch, and you looked at the tip of the torch, end on the torch, well, depending on the size of the torch, it might have 4 little holes and 1 bigger hole in the middle. And the 4 holes here, if it's oxyacetylene cutting or oxy-mat gas cutting, if I look at this sideways, I'll have these little holes, and I'll have a little flame, a little oxyacetylene flame, may only be about 1/8 of an inch long, 3 millimeters long. And if I just touch that, not to a piece of hot steel, but a piece of cold steel, with this iron oxide layer. By the way, rust is Fe2O3. And that's actually called hematite. This is called magnetite. Remember when you played with magnets and black iron powder to make little faces, you know, when you were a kid in that little plastic thing? That was magnetite powder. Okay, it's magnetic. This is not magnetic. So this is called mill scale. You ever heard of black iron pipe? That's what you have in the basement in your boilers. It's got mill scale on it. It forms at about 1,000 degrees Fahrenheit. This forms at room temperature in the presence of moisture. This forms at higher temperatures, generally where there is no condensing moisture. You're well above the steam temperature. Okay? And FeO, which you might have, forms at even higher temperatures in the steel mill. But usually you have mill scale or you have rust, but it's not rust that's forming within seconds. It's Fe3O4, and it's forming at high temperatures within seconds. This forms within minutes, okay, or hours, depending on the moisture. In any case, I have these little flames, and these little flames, before I hit it with the jet of oxygen, so this is oxygen and fuel in a pure premixed flame, just like my little torch there. If I heat up that surface to the point where it's just starting to bubble, and when I look at it, I always like to put the tip of this just barely touching the surface of this steel. And I look at it until it seems like it's starting to shimmer or bubble back at me. It's not big bubbles, but maybe it's just light reflection. But it changes its appearance. I'm looking through some welding goggles, not deep goggles, but you know, just things, because when I turn this on, it's going to get pretty bright. But just good sunglasses, if you will. When I see the surface start to change its appearance, this has gotten to the point where that Fe3O4 is now capable of being blown away by the pure jet of oxygen. And I have another trigger on my torch that opens up this. I pull the trigger, and immediately, within milliseconds, I blow right through here, because there's no boundary layer. What happens to the boundary layer here? It's pure oxygen in contact with steel, but the oxygen reacts to form a liquid. There's no gas boundary layer. I got rid of the boundary layer, and now this thing is no longer 2 to 10% efficient in heat transfer to the surface. It's near 100% efficient. I'm burning the iron to iron oxide. It literally is burning of steel. Okay? I'm burning it to iron oxide, and if it's now nearly 100% efficient, if I go back to this, if I go from 2% efficient to 100% efficient, I get almost 2 orders of magnitude. And if I calculate the relative melting efficiency over this little area and do my mass balance and everything, I will get heat transfer efficiencies in burning equivalent to about 100,000 watts per square centimeter. More intense than a carbon arc, than an arc weld. I can blow metal out of there faster than I can arc weld when I'm oxyacetylene cutting. The thickest I've ever seen cut, personally, is about 12 inches. That 14-inch piece of weld that I brought to you, the guy had this truck of compressed oxygen, and he had 2 propylene tanks about this big, and he had a lance that was basically that would light off the propylene just like this. Now the whole lance was about that big around. He wasn't making a small cut, he was going to be making a big cut. And the hole was probably a half-inch hole of oxygen, and he would warm it up, take about 30 seconds to heat this surface, and then you turn on the oxygen and you should have seen the sparks. It looked just like 4th of July, okay? And he was wearing, leathers and everything. So he was completely covered with a big mask and everything, because the sparks were going everywhere, okay? But it would burn through, and he was just melting big 6-inch gobs of this forging press. And we got something that only weighed about 3 tons when we were all done. And we took it to General Electric Research in New York, and they cut it up into smaller sections. I don't know if it's General Electric Research, but anyway, somebody. Might have been Xerox. Oh, it's Kodak. I think it might have been Kodak. Anyway, not everybody has a saw big enough to cut that stuff. We sawed it up, and we had it sawed up, and then we cut it, and you saw the weld. But I mean, they were cutting out blocks like this. Actually, the block we actually ended up using was about 3 times the size of this cart, okay, in volume. But anyway, so you can cut that way, and if you cut that way, you can get different qualities of cut. This actually is an American Welding Society standard oxyacetylene cutting plastic gauge, and it shows you sample 1, 2, 3, or 4 for the smoothness of the cut. And the sample 1 is a very rough cut. I've seen rougher cuts, but you can see how rough it is because you're just blowing liquid away.
When you get to really thick metals, is it, what limits the thickness? Is it just the velocity of the oxygen?
Yeah, the velocity of oxygen and the size of this torch. The thickest I know of is somewhere between 36 and 48 inches thick. Okay? If you have a big enough oxygen lance behind you. In the steel mill, they might be cutting these slabs that are coming off the casting furnace, and they're typically 12 inches thick. They don't need to preheat them with a little flame because they're solidified. They just solidified. They're already hot. And you hit them with a pure oxygen lance, cut right through them. So the guy's just got a great big pure oxygen torch so he can go around, you know, and wherever it is, he just slices right through it, and it can cut through this at probably several feet per minute through 12 inches of steel. Yep.
How does one vary the roughness of the cut?
It has to do with using the right size orifice, getting a good torch that gives you a nice laminar flow jet of your oxygen, right size oxygen, right size pressure, and the best thing is to actually have something that's moving the torch along. Okay, rather than doing it manually. I mean, the rough one is probably done manually. The very smooth one, and I'll show you. Well, here's I think I got one here. It's not plasma cut. Yeah, this is plasma cut. It also has to do with the intensity of the heat source. You don't have to use fuel gas. You can use lasers. They typically don't use punch presses anymore, mechanical punch presses on sheet metal. Most of the sheet metal cutting is done on a laser now, a laser oxygen cut. Because you can have a 500 or 1,000 watt laser, and this is laser cut. And if you look at the surface, they actually start in the center, and the laser cuts so fast, this thing can be cutting at 20 inches a minute, or 50 inches a minute, depending on the thickness of the steel. They actually start in the center so that you don't get a spot where you first start. And they get out here, and then they run around in a circle to cut a hole in a piece of sheet metal. And the equipment for this is basically the same thing as the biggest uses for laser cutting are for cutting cloth for your clothes. Most of the clothes, your shirts and whatnot, are cut with lasers. And you lay out the cloth flat, and you have a laser come along, and the laser heat just burns right through the cloth. Okay? You don't really see the burn marks because the laser's so fast. There, they may be going 1,000 inches a minute. Okay? But for steel, they actually have the laser at high heat intensity, very high heat intensity, so they can go even faster, and an oxygen jet. And you look at the surface of that thing, and that's, you can see the mill scale on it, but other than that, you couldn't cut it any finer. You know, that surface is beautiful. You take the mill scale off, and it's really a question of the surface roughness will be whatever you ground the mill scale off with. Okay, the grinding rid of what you ground off. So you can get a very smooth cut. Yeah.
So is your cutting then limited by how fast you can remove the material? You said 36 to 48 inches. I would imagine by...
That's thickness.
Right, the thickness. Okay. So I would imagine the problem you're having is the melted molten steel isn't being removed out of the steel, so you can't burn past the oxygen.
You're blowing it out the bottom and of this thing, and actually, it's actually an intermittent process. And people taking high-speed movies, they look down the cut with high-speed movies. And in fact, Brian on Wednesday, I should be here tomorrow to lecture, but Brian on Wednesday might be a good time to show him the Japanese 1980 film on laser and electron beam. And actually, at the end of that, they actually show you electron beam or laser beam cutting. And the process actually is the intermittent process. You will ignite the iron with the oxygen jet, and that thing actually burns down. You can actually see a wave front propagating down and blowing slag out the bottom. And then another one starts. And sometimes you have 2 waves in succession in the thickness of whatever you've got. Okay, but it's actually, it looks like a continuous process to you. And if you run it at the right speeds and the right pressures, you can get a very smooth surface. I actually should have brought in my HY80 piece because there was an electron beam, not an electron beam, but Oxyacetylene cut surface at electric boat, they know how to get the right pressures and stuff for cutting 1-inch thick steel, and it's absolutely smooth. Okay, it's better than sample 4 of that little plastic American Welding side. You can get a beautiful oxygen cut surface, but you do have to worry about the slag at the bottom, and sometimes you'll get little drops of slag that a guy has to come along with a grinder and grind off, which is a little bit of a pain in the neck. You had a question, then you had a question, then you had a question.
Now, I thought today if we were looking for smoothest of cut, we'd go with the water jets, isn't that what they're using now, shipyards?
People do water jets, but they also, the biggest thing is plasma cutting, and I'm gonna talk about that in a second, okay? But
Well, we're not
we'll
gonna
get
talk
there.
about water jets in here, right?
We can talk about, I'll talk about water jet in just a second, yeah.
Just gonna ask about
We're gonna ask about
water
water jet. You were gonna ask about water jet? Yes, you were gonna ask about water jet.
Do they have an issue with those, the small holes clogging up with the, especially when cutting high thicknesses? Because I remember when we were welding, there was a lot of blowback in those.
Yeah, if you get a lot of blowback, if you're not running the process, if you're running it manually and you get some sparks in here, and we can talk about why you get a little explosions, actually you get carbon monoxide bubbles form in here. And you get little sparks. If you ever seen by Oxyacetylene weld, every now and then you hear a pop. And if you actually plug up some of these things, they actually have little round files. It's nothing more than a wire with rough surface, but it's got a file surface. And you have to go in there and clean out your holes every now and then, because they'll get clogged up and things. So yeah, you have to clean it. In fact, a good manual oxyacetylene cutter, first thing he does before he uses his torch is he pulls out his little round files and he cleans those holes, because he doesn't know what the condition was from the last time. If you got some spatter that got up in the hole, you don't have this good laminar flow, and you're going to get a lousy cut. So a good guy goes and cleans out the hole with a file every now and then. Okay. Okay, let's talk about water jet cutting. You use high pressure water jets for your cleaning the siding on your house or washing your car or whatever, and you can get these things up to 3,000 psi pressure. Well, 3,000 psi pressure, you can cut through wood, and it's just basically the force of or plastic. It's just the force of the high pressure water just cutting through it, just like the Grand Canyon, but it took the Grand Canyon longer, okay? But it's also a bigger cut, but it's just energy momentum, okay? If you want to cut metal, well, you can't usually cut metal with its strength and ductility with water jet unless you want to wait a while, like years, okay? So what they do is they put an abrasive slurry in there of aluminum oxide. So now you're sanding through it, but at very high speed. Now there is a water jet cutter over in mechanical engineering here somewhere. I've never used it. Which lab? It's Populardo in the basement. So they've got a water jet cutter that can use slurries, and typically the tips on these things are sapphire. Okay, you can grow sapphire $10 a cubic inch. Okay, and so they make the tips out of sapphire because sapphire is second only to diamond in hardness, and you can run silicon carbide or aluminum oxide through there and not wear out the tips. If you try to use a copper tip, you can cut through the copper tip faster than you cut through the steel. So most of the water jet metal cutting tends to be fairly expensive. You wear out tips every 15 or 20 or 30 minutes, and they're not cheap tips. They're not expensive, but they're cheap. So water jet cutting is great for plastics because it really is just water with no slurry, no abrasive. You can cut wood, you can cut a number of relatively soft materials. If you want to go to metals, you really have to use a slurry, but you can cut very hard metals because you're abrading through them. It's just a grinding wheel made out of water. Okay, that answers your question on water jet cutting. And they are using more water jet cutting because of the precision of the cut and some other things around corners and stuff. Question.
It's kind of off topic, but if I can get my wife a cubic inch sapphire, she'd probably be kind of happy. If it only cost me $10,
Oh, you can buy a couple $100. I just saw something in Parade magazine yesterday. You can buy emeralds for $200. These are real emeralds, man-made.
$10 is a lot cheaper.
If you want sapphire, they will sell you these. They sell artificial diamonds, which are not diamond. They're cubic zirconia usually, but they actually sparkle more than real diamonds. Okay. And they say, well, cut glass. Yeah, well, cubic zirconia is harder than glass. So they can grow these artificial gemstones can be grown in the laboratory today. even diamonds, they can make gem quality diamonds that are 1/8 of an inch in size. But, I mean, a lot of this stuff, now De Beers and other people market the beauty of natural diamonds, okay? Because you can actually make diamonds cheaper than you can go and dig them out of the ground. But they're not natural, and therefore, same thing, actually. We can get it that. But sapphires, emeralds, rubies, I mean, ruby lasers, right? So yeah, if you want a $200 1-carat gemstone, sapphire, emerald, ruby, you can get them. But they're not natural.
You don't know who knows.
So, if that's what you want, you can get them. But the jewelers are poo-pooing them because they kind of cuts into their margins. Okay, so far as other cutting processes. One of the problems with oxyacetylene is you've got this slag that shoots out the bottom, and you form lots of slag, and environmentally it's actually not as fast as plasma cutting. This is actually plasma cut, and came from the plasma cut folks. You can't, let me back up and tell you which metals you can oxyacetylene cut. You can oxyacetylene cut steel easily, and titanium to a certain extent. But you generally, the rule is the metal has to have a metal oxide that melts below the metal melting temperature, and that's true for iron. And iron is 95% of all metal made, so that's a good thing, and that's why we use oxyacetylene cutting. You cannot oxyacetylene cut aluminum because the metal oxide melts at 2000 C, the metal melts at 660, and the oxide will not blow away as a liquid before the liquid blows away. So you can just melt through and make this lousy looking cut in aluminum. Or magnesium, the same thing. Or chromium, stainless steel, is the same thing. Titanium, you would say you can't flame cut titanium, but in fact you can, and I didn't bring a flame cut piece of titanium. I'll have to bring it tomorrow. The problem with flame cutting titanium is it will fill up the room with smoke, even if you got blowers on. I mean, it just smokes really bad. I remember my first research contract when I came as a young assistant professor in the 70s, starting in August of '77, was welding of heavy section titanium for the Office of Naval Research. This was before the Alpha Sub and stuff. And we had some 1-inch thick titanium when we were in the lab cutting one day. This is before you had quite as many environmental restrictions, and we had the blowers on. But there was still some smoke getting out in the hall, and my office wasn't right across from the lab then, someone else's office, and there's a secretary who's still around, but she's no longer in that office. But she complained to the property, to the health and safety guys, that there was smoke coming from my lab. So the safety officer comes over, and he asks, he comes in, he sees Bruce, the technician at the time, working there. He says, "What's going on here?" And Bruce says, "Well, we're flame cutting titanium." And the safety officer says, "What kind of lab is this?" Bruce says, "It's a welding lab." He says, "Oh, well, what do they expect to come out of a welding lab?" Other than smoke. So he walked away. Nowadays, we probably take me away in handcuffs and everything because there was smoke. Okay. Anyway, titanium smoke is not particularly harmful, nor is iron oxide smoke. It's kind of jumping ahead to fumes and gases in welding, but iron oxide is actually used as the non-toxic control by the medical people over here at Harvard School of Public Health. They actually inject iron oxide into the rat's lungs, and it doesn't have any effect medically on changing the chemistry of the body. If you put enough in, the rat will suffocate, okay, from too much oxygen, too much solids in the lungs, but it will not be a chemical reaction. Now, if it's stainless steel fumes, it turns out you do get some chemical reactions going on, and there's things like hexavalent chrome that you have to worry about and stuff. Titanium is also considered fairly non-toxic. And you can flame cut titanium, but it has to do with not with the fact that titanium melts, oxide melts, but titanium will dissolve its own oxide at high temperatures. In fact, if you get above 900 C, these are temperatures in centigrade, if you get above 900 degrees centigrade, titanium will burn, just like magnesium or aluminum will burn in flares. titanium burns almost as hot as magnesium and aluminum. And they have had jet engines in the Air Force that got to above 900 degrees in the compressor section. They're not supposed to. They're not supposed to get above about 600 degrees. But they had something go wrong, and they actually started a titanium fire, and just like the Belknap. Okay, so if the Air Force gives you a hard time about the Belknap, ask them about their titanium cores, okay? Because they wipe out the whole engine. At least the Belknap is still floating, right? When you lose the engine, you tend not to fly quite as well. In any case, so one of the problems is you can't cut a lot of other materials like stainless steels and things. And so people use plasma cutting. Now plasma cutting is, so we're running out of time. I'll pass these around tomorrow, but plasma cutting is basically like a jet burner. You set up an arc and you shoot it out of a little orifice, very high velocity, and you blow the metal away. And plasma cutting has one distinct advantage. You can actually do it underwater. So one of the problems is oxyacetylene of titanium or iron, you generate lots of smoke. And the environmental people don't like that. Plasma cutting you can cut underwater, and so you collect all the smoke in the water. You end up with dirty water when you're all done, which you can filter out all the oxides. And so plasma cutting is replacing oxyacetylene cutting in many applications because of environmental things. It also has advantages in speed, it has advantages in the smoothness of the cut, if you do things properly. It also has advantages that you can cut virtually any material.
Does cutting underwater reduce the efficiency of it? I mean, losing
No.
heat and water?
No, we can talk about that tomorrow. When I see I'm running out of time. Some people have a class, right?
Tomorrow, initially we thought we had another quiz tomorrow.
Oh, okay.
So we're gonna.
So if you want to skip class tomorrow, we can skip class tomorrow if you have a class, that's okay.
No objections?
No
All right.
objections. Okay, so you can shut it off, Ryan.